Hello everyone, my name is RJ, and today we're going to be discussing orbital mechanics. So I think the easiest way to start is just take a rocket, point it straight up, and see what happens. So let's give it a go. So here's our view from space. You can see that faint blue arc coming out of the right side of the planet. That's our trajectory. We're still accelerating, so it's going to keep getting higher and higher until we stop, and eventually we'll reach the peak and start falling. But what if we don't want to fall back down to Earth? If we wait until we get to the top of that peak, called the apoapsis, and then we fire our thrusters not up, but prograde, or to the east in the direction that the Earth rotates, we can make ourselves fall further and further to the east until we miss the planet entirely. Achieving orbit isn't really about not experiencing gravity, it's really about falling continuously, but also missing continuously. Okay, so getting to orbit was easy enough, but what if we need to get away from the planet entirely? How fast do we need to go? The term for that speed is escape velocity, and it is equal to the square root of twice the universal gravitational constant times the mass of the planet over the distance from the center of the planet. Or, if you're already in a stable orbit, escape velocity is your orbital velocity times the square root of 2. So here we are in orbit. Note our orbital velocity is 1880 meters per second. If we multiply that by the root of 2, we get about 2660 meters per second for our escape velocity. As we fire our thrusters, watch the speed and trajectory to see when we escape orbit. Right on the money. But there's always a bigger fish. Now that we've escaped the planet, we're still in orbit around the sun, and it would take even more energy to escape its gravity. Okay, so maybe flying around the sun untethered is a little bit too much separation. What if we just want to change orbit? For that, we want a Hohmann transfer. Starting in our circular orbit, we fire our thrusters with the nose of the ship pointed prograde, or in the direction we're orbiting. This pushes our circular orbit into an elliptical one. The more we push, the higher our apoapsis gets. Our periapsis, which is the closest point we will come to the planet, doesn't change yet. Once we orbit around to the apoapsis, though, we fire our thrusters prograde once again and push out our periapsis until the peri and apoapses are both roughly the same altitude again, and our orbit is circular. The same process works in reverse. You can fire your thrusters in a retrograde orientation, or opposite the direction you are orbiting, in order to lower your orbital altitude. Watch as the space station in the inner ring spins around and catches up to the orbiter in the outer ring. One of the craziest things about orbital mechanics is that when you accelerate into a higher orbit, you actually revolve more slowly around the planet. This can be useful for planning rendezvous between different spacecraft. Now we can Hohmann transfer down and actually circularize into the same orbit as the space station, right beside it. With our burn complete, watch as the orbiter closes in on the space station. Right now, our elliptical orbit will cause us to fly right past the station, but if we fire again to circularize just as we would be passing it, we can achieve an identical orbit. Now it is a simple matter of fine-tuning the relative velocities in order to dock and restock and recrew the space station. When docked operations are complete, we put a little bit of separation between us and the space station in preparation for a deorbit burn. In order to get home, all we have to do is perform a retrograde burn until we are no longer going to miss the planet in our free fall. From there, gravity takes care of the rest as we are used to. Also worth noting, always pack a parachute.